So let's start our talks. Good morning. I am chairman today, so I will probably, you have 45 minutes, yes?
Yes, I guess.
So it's like 10 to 10.
I might exceed a bit, but hopefully not. Anyway, I'll try not to.
Sure, sure. Today's talk is of Takato Yoshimura from the University of Oxford, and the title is Ballistic Microscopic Fluctuation Theory for Integrable Systems. Please.
Thank you. So, hi everyone. Let me first thank the organizers for the kind invitation. It's been a great pleasure to take part in this wonderful workshop, although I'm not really a high energy theorist or string theorist. So what I'm going to talk about today is based on my recent work with Benjamin Doyon, Gabriele Prefetto, and Tomohiro Sasamoto. And the motivation of this project was, at least the initial one, was basically to devise a theory that can describe the large division properties of many body systems, could be quantum or could be classical, in a systematic way. And what I mean by large division is simply, for instance, current fluctuations. So we wanted to characterize the properties of current fluctuations. But as it turns out, not only does this theory, so this ballistic macroscopic fluctuation theory, do the job, meaning that it can describe the large divisions of many body systems in a systematic way, but also it can actually provide a new kind of way to compute quantities that should be also of interest to you. For instance, dynamical correlation functions. So I'm going to put a bit more emphasis on that, and these are basically what I'm going to talk about today. So, to set a stage and to be a bit more precise about what I'm going to do, let me introduce a kind of quantity that I'm interested in. For instance, I'm interested in evaluating this kind of dynamical correlation function that involves an arbitrary number of local observables, these guys, that are inserted at arbitrary space-time positions. And this average is done with respect to, say, local thermal equilibrium, or it could be local GGE if your system is integrable. And it's usually written in this way, where the inhomogeneity, if your system is inhomogeneous, is encoded through here, which is a Lagrange multiplier. Well, in this case, simply the inverse temperature, because H hat is the Hamiltonian density. And the length scale that over which the state is varying is controlled by this parameter small l, which is eventually sent to infinity. So that's the kind of setup. But of course, the theory, ballistic macroscopic fluctuation theory, BMFT, that's the acronym of the theory, doesn't quite allow us to really compute this kind of quantity for arbitrary space-time positions, because that's simply too good to be true. So instead, it demands us to focus on a particular situation, which is what we call the Euler scaling. So we have to take a particular scaling in order for the theory to work. So what would be the scaling? Well, simply stated, we have to take xi's and ti's to be very large compared to all the microscopic scales, but still the ratio of these guys, xi and ti, so xi over ti, should always be kept finite. So this is the kind of scaling that I'm going to work with. And basically all the kind of statements, well, not all, but most of the statements I'm going to make are valid only under this kind of circumstance. So that's something you should bear in mind. But still, I guess it's kind of interesting that if you focus on that kind of situation, you can say really a great deal about this kind of interesting quantity. All right. So before jumping into the detail of the theory, perhaps it's nice to just, at least try to do the usual thing and see what we can do about it. So what I mean by that is just to write down the usual Feynman path integral formula for this kind of dynamical correlation function. Let's say, for simplicity, evaluated with respect to some thermal equilibrium. And it should read like this. But I guess the moment you write down this kind of expression, you realize that you're stuck because you don't know what to do. I mean, how to proceed. Because, for instance, these local observables are supposed to be quite complicated in terms of the fundamental field. And also, if your theory is non-trivial, I mean, not a free theory, then the Lagrangian is probably complicated. So, I mean, in any case, you know that this isn't quite the way to go forward if you really want to compute this kind of thermal correlation function. So the question now is, what could we do about it? Could there be a more efficient way to compute this kind of correlation function? And the answer is yes, if you really work with the scaling that I just mentioned, because on that scale, the only only relevant degrees of freedom that matter are those that are protected by the conservation laws. Meaning that, for instance, energy conservation law or the momentum conservation law. Or if your system is conserving U1 charge, then of course that should also be taken into account. So, but yeah, right.
Do you assume also that beta is large?
Beta is large.
I'm asking.
No, we don't really assume that it is going to be valid for arbitrary beta, so long as it's far from.
That T is large. If T is large and then there is some periodicity in beta, then beta should be also large.
Okay, maybe that's because I'm writing this way, so perhaps this isn't quite nice. Might not be a nice way to write down the path integral formula. I mean, sorry, the correlation function. I mean, what I can tell you is that the theory that I'm going to tell you about is going to work for arbitrary temperature, so long as it's sufficiently far from the ground state. But time should always be large. That's the kind of condition you have to work with. Maybe that's not really quite clear from this expression, but that's the condition that I would demand. Okay, so, okay, so the idea is somehow we have to exploit this kind of fact, but that's easier said than done, and the crucial point here is how to implement, that kind of idea. And it turns out that this theory we recently devised can precisely do the job. So nicely implement this kind of idea, and as a result, it provides a new way to compute the dynamical correlation function, for instance, like this, for, again, a large x and t. And a remark here is that there would be, so we need to put some kind of data to do this kind of theory, and there is only one kind of data that would be required, which is the hydrodynamics of the theory. So said in another way, if you know the hydrodynamics of the theory, you're in business. You can do this ballistic macroscopic fluctuation theory to compute dynamical correlation functions. So we have to know the hydrodynamics. That's the kind of starting point. And okay, let's talk about then hydrodynamics. Not sure how many of you are familiar with the notion of hydrodynamics. It's not that complicated.
Excuse me. I have also a question.
Yeah, sure.
But since the system is integrable, in principle,
well,
the
so
number.
far I haven't really specified to integrable systems, but yeah, later on I will focus on integrable systems. But what I have been saying works for non-integrable systems too.
All you said so far is about any theory, not necessarily integrable.
Indeed. So long as the system has translation invariance, meaning that it preserves momentum cause of it.
Then my question is premature, but maybe you still will answer it later. That why at all you expect the ergodic behavior, because you have as many conservation laws as the degrees of freedom. So what does it mean then?
Oh yeah, sure. That's a good
Thanks.
question. Of course, I forgot to tell you. Thanks for pointing that out. Of course, in the case of integral systems that are presumably your favorite kind of systems, you have to put all the kind of conservations that are coming from integrability. So not only the energy or momentum, these kind of low-lying conservation laws, but also you have to put all the kind of higher spin conserved charges. They have to be equally treated for the theory to work. So yeah, that's what I'm going to do actually later. So, right. So let's then start with considering a translation invariant many-body system with n conservation laws. And for the moment, I wouldn't specify the number of conservation laws because that's not really important here. But I'm implicitly assuming that, well, yeah, non-integrable systems, but actually, well, it doesn't matter. Well, it doesn't really matter, actually, if it's integrable or non-integrable. So anyway, the initial condition that I have in mind is, as I said, like this. So it's some kind of local GGE or Gibson symbol. Again, the inhomogeneity is encoded through the Lagrange multipliers. Now, in order to define the key object in hydrodynamics, I have to define a procedure called cross-grading first. So what I mean by that is as follows. So imagine you have some local observable that is inserted at some space-time point, x and t, here. And you take some extended space-time domain that includes this space-time point. Or in this case, for simplicity, I'm taking a square, but in principle, it could be any kind of domain. And this square is with size large L. And all we've got to do here is to take an integration over this domain, which we usually call field cell because it looks like a cell. And by doing that, we are basically washing out all the kind of microscopic physics that is happening inside of the cell, which we are not really interested in. So we want to kind of, preempt the kind of the possibility that there could be some kind of consequences from microscopic physics entering in the final result, which we wouldn't want to happen. So anyway, we have to do this kind of cross-graining just to wash out the microscopic physics. And there is an important inequality that we should have in mind, which is also sometimes called separation of scales. So the first bit is stating that the size of the cell, field cell, should be sufficiently larger than the microscopic scale, which is usually set by, say, in the interparticle length. But still, it should be small enough compared to the macroscopic scale that is set by this parameter. Not sorry, parameter, but it's a scale, small l. So this should, for hydrodynamics to work, this kind of inequality is always implicitly assumed. All right. Now, having defined this quantity, sorry, not quantity, but a procedure, we can define the key observables in hydrodynamics and also in the BMFT. So to define that, we have to just put these macroscopic coordinates in the arguments here for the mesoscopic observables, mesoscopic cross-grained observables. And these macroscopic coordinates are there in order to enforce the Euler scaling. So I guess at the beginning I said what I mean by the Euler scaling is that xi and ti being very large, whilst their ratio is always kept finite. But this is a bit more precise way of defining the Euler scale because it tells you that the way x and t are sent to infinity is controlled by this parameter that enters in here. Okay, so this is the kind of key observable, mesoscopic observable that I'm going to be interested in. And I'm going to also treat them as fluctuating variables. And the fluctuations are going to be set by the initial condition. And this is, of course, again, a non-trivial remark, because supposedly these guys can fluctuate in whatever ways as they please. But the point here is that we are working with a particular situation, which is really a large-scale space-time. And the idea is that on that scale, all the kind of fluctuations that would contribute to these mesoscopic variables with macroscopic coordinates would be the initial fluctuation. Of course, there could be other sources of fluctuations, for instance, dynamically generated fluctuations, but they are usually subleading. And the magnitude of these guys are like square root of L, whereas these are linear in L. So they are not really going to matter so long as you take the large L limit. All right. So, okay, there are a number of interesting predictions coming from hydrodynamics. One of them is like this. So if you want to take a local average of these mesoscopic variables, again, just to reiterate, this O bar is coming from this cross-graining procedure. A priori, this is quite a non-trivial kind of average, but what hydrodynamics tells you is that this can actually be written as an equilibrium average. But of course, there should be some kind of space-time dependence somewhere, otherwise it's going to be constant. And the way it's going to depend on space-time is through the Lagrange multipliers. So the only things you've got to do now is to know how these betas are going to time evolve, which I guess is a much simpler kind of task than really working at. Right. Small L is entering in this initial state. So it's a kind of scale that sets, it's a scale over which the state is really varying. So if you really take L to be infinity, then just a homogeneous case. But if you put...
So I'm confused about the following. You average on a capital L. You average on a capital L?
No. I average over this initial condition. So this is... Yep, O bar, but okay, this isn't really the averaging. This isn't quite what I mean by averaging. This is just a cross graining. It's just integrating over space.
Okay,
yeah, exactly. So the averaging contains the small L, yes.
No. Cross graining contains large L, but your key formula of the L contains small L. Yeah, so this formula of the line different.
Yeah.
The small L.
Yeah.
But bar contains large L.
Yes, okay. O bar contains large L. So, okay, now the point is, they are in any case, they are both meant to be sent to infinity eventually, but this relation that is large L is always smaller than small L should be satisfied. So, I'm not sure what's the kind of problem that you have here. No, the point is, it's just that you prepare these cells, right? So they are like, the compositions of the space into the cells. And you take cross graining. So it's, in a sense, it's like replacing each cell with this new kind of point. And this point is now taken to be macroscopically large. That's the kind of procedure what I'm doing here. So it's like cross graining plus replacing the coordinate with the macroscopic coordinate. Okay?
LS stands far away from its T. It's just on that other wall. If this one is capital L,
Yeah.
small L is sensitive to that other. How they are related?
So again, the small L is the length scale of the initial condition, yeah? And the cell is this big, which indeed is still big compared to the interparticle length, so it contains a sufficient number of particles. But the point is, if you look at the scale that is comparable to the small L, things are still varying smoothly. Okay? Anyway, hopefully I can make things a bit more concrete later, but are you still confused? Okay. Sorry. Right. So where was I? Yeah. So as I said, I can write down this kind of local average in terms of the Lagrange multipliers that are dependent on x and t. But the point is, you can also write it in terms of, as a functional of q's. So charge density averages are defined in this way. And this is because in equilibrium, there's a bijection between the set of betas and the set of q's. So by using that, you can also write down the local average like this. So this is what we usually call localization of averages. Right. Now, as I said, the problem now boils down to get to know how Qs or betas are going to time evolve. And this is precisely what is prescribed by the hydrodynamic equation. So, for instance, hydrodynamic equations can be written this way, where the matrix A is defined in this simple way. It's a derivative of J with respect to Q. And the C matrix is the usual susceptibility matrix. Now, there is another equivalent way of writing down the hydro equation, which is in terms of the Lagrange multipliers. And as it turns out, this is going to be useful for my purpose, so I'm going to use this extensively. Now, we know how to characterize the space-time profiles of local observables. I mean, so long as, again, we work with a large-scale space-time. But the real question now is how then the fluctuations propagate in space-time? And or to be more precise, according to which measure would O of x and t fluctuate? So that's a question to answer. But to start with, we should first understand how to characterize the initial fluctuations. So the fluctuations coming from the initial condition. So again, the kind of quantities that I'm interested in are the mesoscopic variables defined in this way. And thankfully, we know that how to characterize the initial fluctuations because people have worked on it before. So it's simply that they're going to fluctuate according to this measure, dp ini, which is given in this way. So d mu is simply a flat measure. It's a measure that you usually use in your functional integrations. But I guess the non-trivial bit is in here. So this curly f, which is given in this way. And this guy is called the large deviation function. And here, for instance, S is the entropy density. And all the quantities that are coming with the subscript ini are supposed to be evaluated with respect to the initial condition. So again, just to reiterate, I guess it is quite non-trivial that these guys should fluctuate according to this in this large deviation fashion. But well, this is all because we are working with this particular situation, which is large scale. So if you depart from that kind of situation, this isn't quite true. But this is good news because we can exploit the fact that this is taking this form, which is exponential of L times something. And it's going to be really to help us carry out the computation. So I'm going to exploit that. Just to check this is consistent, because this is, a fluctuation that is around the mean value, which is captured by hydrodynamics. So if you take the saddle point of the path integral like this, it ought to give you back the result of hydrodynamics. And indeed, it does. One can easily see that it does give you back the hydrodynamics. So this is consistent. So the question is, how are we going to generalize this initial fluctuation measure to the measure for the fluctuations of full-fledged space-time independent charge averages? Again, this is a mesoscopic coarse-grained variable with this macroscopic coordinate. So actually, we don't quite have an answer. I mean, in the sense that we don't have a derivation of the statement I'm about to make, but we have a physically sensible reasoning. So to know the measure that I mentioned, we have to assume something. And the principle that we are going to assume that it holds is what we call local relaxation of fluctuations. So what I mean by that is as follows. So fluctuating variables, these guys, the variables that I have been talking about, actually do not fluctuate independently. Well, supposedly they are, but they would be, but the claim or assumption is that they actually do not fluctuate independently, but rather are fixed functionals of fluctuating charge densities. So in terms of the equation, our assumption is this one. So question is, how are we going to determine this functional form, which is yet unknown? We can luckily do it quite easily by invoking the fact that at t equals 0, we can invoke this kind of path integral formula because we know that the initial fluctuation measure should be given in this way, as I stated in the previous slide. So we use this fact, and by taking the saddle point, we can actually see that this functional form is the same as what we used for the hydrodynamic in hydrodynamics, meaning that what we used for this kind of expression, which is a local relaxation of averages. And this is, I guess, quite non-trivial in twofold sense, because firstly, again, it doesn't have to be this way. They can, in principle, fluctuate in their own ways. But our claim is that, well, on this scale, again, everything pertaining to the Euler scale physics should be governed by the conservation laws. So in that respect, it is not too outrageous to assume this kind of form. So that's the kind of reasoning that we have. But on top of that, somewhat surprisingly, we can also see that this functional form is completely fixed by hydrodynamics. So the same kind of function form that you used in evaluating the mean values. So there's a nice parallelism between the local relaxation of averages and the local relaxation of fluctuations, which I'm going to really make full use of. Okay, so now we are in the position to write down the measure that I have been mentioning, which should read like this. So the first two bits are the same as the initial fluctuation. The third one is the new one. But it's quite trivial because it's just there in order to enforce the continuity equation. But the non-trivial bit here is that the current there is supposedly, again, could be independently fluctuating. But the assumption we just made tells you that, well, that's not quite the case, but the way the current fluctuates is dictated by the way Q is going to fluctuate. So we have to put the local relaxation of fluctuation, so the principle, in here, and we have this measure. So now we're in business. For instance, we can compute the BMFT average, so average with respect to this measure in this very simple way, where in the second line, I just exponentiated this delta function. It's like a Laplace transformation, like this. And of course, the main claim of the BMFT is that this BMFT average should be identified as the local average. So what we have to do now is to evaluate this kind of path integral. But the real point of the BMFT is that you do not actually have to evaluate this kind of path integral formula. This is because eventually, if you take this limit, small l to the infinity, everything is going to be dominated by the saddle point. Well, I said saddle points, but actually, I should remember this as because there will always be one saddle point in here. So how are we going to see that? Let's say if you want to evaluate this kind of, average of this kind of observable, you might be tempted to put that in this formula. But I guess you wouldn't then know how to proceed because it doesn't really tell you anything. And as it turns out, that's not quite the right thing to do. What you have to do instead is to put this guy, exponential of L times O, and evaluate this path integral formula. The good point of this trick is that everything is now of this form, exponential of L times something. So if you take large small L limit, of course, it's going to be dominated by the saddle point. So you can just pick the contribution from that. And that's going to spit out some kind of number like this, where this curly O is defined in this way. So just to remind you that this curly O of Q dot 0 is the large deviation function that I defined in here. And this Q star is the minimizer of the BMFT action. So in order to know the equation that is satisfied by the Q star, you have to take a variation of this action with respect to Q and H. And if you do the latter, you immediately see that Q star has to be always the solution of the Euler equation. So this is always satisfied. So what we can infer from this is that the effect of inserting the operator here, which can be also thought of as modifying the measure, is encoded solely through the boundary condition or the initial condition of this Euler equation. Or actually, it's going to be a coupled Euler equations, but anyway. So we are going to see it. To make things concrete, I'm going to focus on these two quantities. So the first one is, as I advertised, the Euler scale dynamic equation function. Right. But the second quantity might not be so intuitively clear to you. Well, it's actually a very physically important quantity called scaled cumulant generating function. So it's basically a quantity that tells you how the currents are going to fluctuate. So it is also experimentally relevant, and anyway, so just to check the validity of the theory, I'm going to evaluate these two quantities. And to do that, you have to choose O, so the observable this one, in these two ways. Okay, where lambdas are simply some parameters. Okay, and you immediately realize that if you follow the logic of the BMFT, these two objects should be given in these fashions. So I'm going to see how we can really compute it. Okay, now let's start with the current fluctuations. Okay, so the scaled cumulant generating function, which is simpler. So in order to know the equation satisfied by the Q star, we have to, as I said, take the variation of the BMFT action S, which reads like this. So if you solve this equation, then you know the full profile of the Q star. And once you know it, you can plug that into this formula. I didn't write down the derivation. It's just a consequence of the simple manipulations. So the scaled cumulant generating function defined here is written in this way. So if you know the full profile of the Q star, you can plug that in here and compute it very easily. So this is a much simpler way to compute this kind of object. But what we are really after here is the dynamic equation function, which is, okay, for simplicity, let's focus on the two-point function. And this is given by in this way. And again, by doing some simple manipulations, you realize that it's also written in this way. So we have to evaluate this. And Q star is going to satisfy this BMFT equation, which is slightly different from the current fluctuation case, because obviously we are talking about different kind of object. But a surprising point here is that by doing some formal manipulations, we can see that the BMFT actually predicts something quite non-trivial and a new kind of physical phenomenon, which is as follows. So imagine you try to evaluate this kind of dynamic equation function, and note that the time coordinates are the same for two observables. So they're evaluated on the same time slice. And this guy is going to behave in this way, which is highly non-trivial, because the conventional wisdom of hydrodynamics tells you that we would only have this first term, which ensures that if you start out with some local equilibrium, then this will, the structure of it will remain intact. So at any time slice, you can effectively assume that the local equilibrium is realized on each time slice. That's the kind of message you can get by seeing that this is the only kind of quantity that is appearing here. But the BMFT predicts otherwise. There will always be an additional contribution like this, which is going to decay in a so much slower way. So in terms of microscopic coordinate, this is going to decay like 1 over x, as opposed to the exponential decay coming from this one. And this is quite interesting because, even if you start out with some initial condition that has no long-range correlations whatsoever, this kind of long-range correlations, dynamically generated long-range correlations, could build up just through some hydrodynamic interactions or the correlations amongst normal modes. Well, I mean, normal modes are basically hydrodynamic modes, provided that the system is on some inhomogeneous background. So this is really coming from the inhomogeneity of the system. And actually, there are 2 other conditions that should also be satisfied for this to be happening, I mean, long-range correlation. So the first one is multiple conservation laws. It has to be having at least more than one conservation law. And the one is the interaction. So it cannot be free theory. And the third one is the inhomogeneity. So the idea here is that, let's say your state is homogeneous. And basically, all the kind of correlations that would give rise to, and that would contribute to the dynamical correlation functions are coming from the correlations amongst the normal modes. So normal modes are basically the carriers of the slow modes. And at some time, they're going to be emit. So a pair of them would be emit. And they're going to propagate. And the point is, if the state is homogeneous, it doesn't matter where they are created. Because they, everywhere in the states, they look the same. But if your system, the state is inhomogeneous, then somehow these 2 propagating normal modes retain the memory of where they are created, where they are emit. So this is coming really a kind of physics that is coming from the inhomogeneity. And this, to our knowledge at least, hadn't been really known before on this scale. Actually, people knew that this kind of thing could happen on a different scale, say diffusive scale, but on the Euler scale that we are interested in, this is, I guess, quite new. So to see if this is really true or somehow a kind of, false observation that is made by some formal manipulations, I'm going to apply all this machinery to the BMFT, the integrable systems. Yeah. Okay, so how much time do I have? 7, okay, I have to be then a bit quick. Okay, so to apply this BMFT to integrable systems, as I mentioned at the beginning, the only kind of input needed is hydrodynamics. And if you want to treat integrable systems, then you have to know the hydrodynamic theory for integrable systems, which is, of course, generalized hydrodynamics. Well, maybe some of you, or maybe many of you, don't really know what the generalized hydrodynamics is. So I'm going to give you a brief account on that. So this is a kind of theory that we devised a while ago. And a key intuition behind GHD, generalized hydrodynamics, is that on the large scale, on the hydrodynamic scale, all the integrable systems are going to behave in the same way. And to be more precise, they're going to behave as if they were hard rods. So that's the kind of intuition you can get from working out hydrodynamics for integrable systems. And that is precisely why GHD is so universally applicable to many integrable systems. And hard rods are simply, I guess it's one of the simplest kind of integrable systems. It's just a bunch of rods on the line, and they scatter or collide elastically upon a collision. And interestingly, if you really look at integrable systems on a large scale, they behave pretty much like hadrons. Right. Now, the hydrodynamic equation of the GHD, so GHD equation reads like this. So the kind of beauty of GHD is that now we can write down the equation at the level of quasi-momentum. So for instance, rho theta is the particle, density of particle, whereas effective velocity, which is again labeled by the quasi-momentum theta, is some functional of rho theta, given in this way. And this var phi, this guy, here is, of course, coming from the S matrix. So it's like a derivative of the logarithm of the S matrix. So we have to plug that in here and solve this equation self-consistently. Right. Or equivalently, one can also write down the GHD equation in terms of the betas, as I will do later, by defining the beta theta in this way. Okay. So for practical purpose, I'm also going to introduce the mode that we call the normal mode, which satisfies this kind of equation. And this epsilon defined in this way. So once you know the beta, you can get epsilon by this transformation, where R, the matrix R, is given in this way. So this is a matrix labeled by the quasi-momentum, and as it turns out, it also diagonalizes the matrix A, so Jacobian matrix, and its eigenvalues are the effective velocities. And we call this normal mode because now the velocity is coming in front of the x derivative, and this is going to be important. I mean, at least for technical purpose. And a physically important remark here is that there would be no shock in GHD, meaning that there would be no sharp structure that's going to emerge as a consequence of dynamics would exist. So this is good to know because this basically implies that there will always be a unique solution of the GHD equation. And that's reassuring, and we don't have to worry about the potential existence of other saddle points. So at least so long as, as far as the integrable systems are concerned, you are in the safe position. Now, again, let's start with the current fluctuation. So this is the same thing as before. The only difference is that the indices are now quasi-momentum. And I'm treating them like usual integer indices, but for instance, this guy should be thought of as a direct delta. And here hi of theta, which I redefined in this way, is simply the one particle eigenvalue of the charge Qi. To go forward, we also have to define the normal modes associated to this field, H, auxiliary field, which appeared as a consequence of the exponentiation of the delta function. And the way we do it is based on how we define the normal mode for the betas. So this is the way we define the normal mode for the H. Right. This is just a way of doing manipulations. And we have now this, so two equations of these MPMFT equations can be now written in this way in terms of the normal mode. And the reason why we did this is because we can then use the method of characteristics to compute this kind of profile. And what I mean by the method of characteristics is that if you want to know this kind of field profile, the only thing you've got to know is the profile of this guy at t equals large T. So this is a final time. And once you know that, you can get this field profile, provided that you can evaluate this r theta of x and t. But this is so much simpler task because this is going to satisfy some simple integral equation. So if you solve the integral equation, you can obtain this r theta of x and t and get this full profile. I didn't write down the integral equation satisfied by the r theta, but it's not that complicated. Anyway, so at the end of the day, you reach this kind of, I mean, you can recast the whole MFT equation into this form, which is the GHD equation with some very non-trivial boundary condition. So you have to work out this equation, which is not always feasible, but in principle you can do it. For instance, in the homogeneous case, let's say thermal equilibrium, you can evaluate the Taylor expansion coefficients of the cumulant derivative function, which we call cumulants simply, and they read like this. For example, the second and third one read like this. I didn't really write down some definitions of the quantities because they're not so important. What I want to say here is that simply you can work out. Things could be a bit messy, but in principle you can work out. And these are also in agreement with the previous predictions from different theory, and also agrees with the simulations. And the nice point of the BMFT is that one can also easily extend these things to inhomogeneous cases when the initial condition is, not really homogeneous anymore. And for instance, if you pick this kind of initial condition, which is a particular initial condition, a step profile initial condition, if you like, then you can get this kind of second cumulant in this way, which is somewhat surprising, again, physically, but I guess I don't really have time for that. So I'm going to skip quickly. This is just to show you that it really agrees well with the numerics. And this is just a cartoon picture of the Hadrod system with the Hamiltonian being like this. All right. But what we are really caring about here is the dynamical correlation function. So we can proceed as in the current fluctuation. And we eventually obtain this kind of GHD equation with the boundary new non-trivial initial condition. And after some cumbersome manipulations, you also can obtain the exact formula for the long-range correlations, which are really messy. We have to solve all these things in a self-consistent way. I didn't, again, mean to write this to be informative. This is just, I wanted to say that one can really compute this kind of thing once you're really determined enough. So one can do it. And if you really do it, you get, yes? Yeah, sure. So I'm going to finish in the next slide. Yeah. So these are just the numerical checks for this result, and they really agree very well. Okay, so sorry for the bit of a delay. I guess just talk about the outlook. So BMFT is really a unified theory, so naturally it really opens up a variety of new directions. It would be nice to verify it microscopically because it's a phenomenological theory, and also it would be nice to apply that to a different transport type, like super diffusion, a super diffusive transport, and also it would be nice to say, for instance, compute something of quantum nature, let's say entanglement entropy, like time evolution of the entanglement entropy, or incorporate the quantum fluctuations. They are, I guess, all equally very exciting directions. So anyway, so with that, thank you very much for your attention.
Thank you. So please, questions.
I would like to ask the physical meaning of this capital R operator, because we face with the kind of similar quantity in calculating finite size form factors.
So I guess you mean this one, yeah? It's just a dressing operator. So if you, for example, I guess defined somewhere up here. So if you, for instance, say for some function of theta or phi, you can just apply this and get the dressing equation.
But dressing in which sense? What dressing interaction or
Yeah, dressing
dressing?
interaction. So I guess it's a bit different from the kind of dressing that is usually used in the integrable system community, but this is just a way to incorporate interaction. So what you get as a result is that this guy is going to satisfy some integral equation that looks pretty much like this. So it's just a way to incorporate interactions.
So in finite volume calculations, usually this is how you take into account the finite size effects order by order of the particles. So is it a finite temperature effect here, or what?
Yeah, so indeed, not the finite volume effect, but the finite temperature effect. So it's a way to incorporate the kind of state.
Thank you.
More questions? Actually, I had a question which is maybe a continuation of Zoli's question. Can you play here these games of analytic continuation to beta, to imaginary beta, like we do in homogeneous systems to compute this Alexei Zamolodchikov trick? You compute the thermal equilibrium, then you do analytic continuation to compactified space. Or this inhomogeneity destroys completely this analytic structure.
I'm not sure about this analytic continuation thing. So,
so you have
inhomogeneous,
I don't know how to formulate, inhomogeneous distribution of temperature versus inhomogeneous spatial circle distribution of.
So, okay, you mean the periodic condition for the state, not for the system, but. But what would it mean in this case? It just. I can't quite imagine what kind of state it would be. I mean, maybe it's possible, but and if the circle of the beta is really large, then maybe it makes sense because it's going to be weakly changing. But still, yeah, not sure what exactly it means.
Okay.
Sorry.
Thank you. There is a question there, Benjamin.
Yeah, thanks for the nice talk. It's just a naive question. I was wondering, is there anything interesting? I mean, could it be interesting to look also at theory with non-diagonal scattering? Or
Yeah, I guess you can easily do that for non-diagonal things, systems, because GHD has been applied to non-diagonal theories like a Fermi-Hubbard model. So we know how one can do GHD for non-diagonal systems. So, and as I said, the BMFT requires only the hydrodynamic input. So if you know the hydrodynamics of the theory, you can do it. But I'm not sure what would be, something extra interesting. I mean, if you deal with the non-diagonal systems, I mean, there would be always long-range correlations, like I explained here. But that's not really, to do with non-diagonal scattering or anything. It just it would be there always. So you can do it.
So it's not giving rise to new behavior, or it's more or less the same, you're saying?
I guess more or less the same, but maybe there could be interesting physics that I'm not really aware of. But yeah.
Okay, thank you.
If there are no more questions, let's thank the speaker. Okay, let's start our second talk, please. So Benoit Vichedeau from University of York will present the talk, the Godin model from 3D mixed BF theory. Please, Benoit.
Okay, so thank you very much. So let me start by thanking the organizers for the opportunity to give this talk. So what I want to tell you about is the gauge-theoretic approach to integrable systems, which was proposed by Costello and further developed by Costello, Witt, and Yamazaki, which is based on 4D Chern-Simons theory. So I'll actually be talking about a slight variation of this story, which is based instead on 3D mixed BF theory. And the purpose is that this theory can be used to describe finite-dimensional integrable systems. So it's a very useful toy model for understanding the gauge-theoretic origin of integrability, I think. So the talk will be based on this paper with my student Jennifer Winston. So I'll refer you to it for details on what I'll talk about. Okay, so let me start with a very brief summary by reminding you that 4D Chern-Simons theory is sort of like a mother theory for integrable systems in the sense that it can be used to describe two different types of integrable systems. In particular, if you introduce line defects in the 4D Chern-Simons theory, you can describe in this way integrable lattice models, which are, whose integrable structure is underpinned by this RLL quantum structure. Or more precisely, because I'll be focusing in this talk on classical systems, I should talk about the Sklianin bracket, which is a quadratic bracket in the Lax matrix for the Lax matrix with itself. And another thing you can do from 4D Chern-Simons is introduce surface defects to describe instead two-dimensional integrable field theories, where the integrable structure in this case is underlined by this linear Poisson bracket in the Lax matrix, but with these delta functions because we're dealing with a field theory. Okay. So what I want to tell you in this talk is how a similar story works for finite-dimensional integrable systems with linear brackets for the Lax matrix, where the correct theory to start from is 3D BF theory. Okay? So I want to essentially explain in detail how this construction works to go from 3D BF theory by introducing line defects and gauge fixing to obtain finite-dimensional integrable systems, specifically ones which arise as realizations of Godin models. Okay. So to start with, let me just remind you in one slide, for the purpose of this talk, what we know about 4D Chern-Simons theory and how it relates to two-dimensional integrable field theories. So if you start with 4D Chern-Simons theory on the cylinder times the CP1, which will play the role of the spectral plane, what you do is you start by introducing surface defects, which are along the cylinder and at fixed points in CP1. And then you impose boundary conditions on your gauge field at these surface defects. And after gauge fixing, you find that the gauge field of the 4D Chern-Simons theory becomes the Lax matrix of the integrable field theory in 2 dimensions. So you should think of the field theory as living on the surface defects, which are essentially copies of R cross S1. So you end up with a theory on the cylinder. So there's an alternative approach to producing a large family of integrable field theories on the cylinder, which is to use affine Godin models. So this is more rooted in the Hamiltonian formalism. And the idea here is you start with a Godin model based on an affine Kac-Moody algebra. So we heard about Godin model, the Godin model yesterday in Ilya Burik's talk. This kind of Godin model will be one associated to an affine algebra rather than a finite dimensional algebra. And the point is that to get a specific integrable model, what you do is you choose a realization of your affine Kac-Moody algebra at each site of the Godin model. Okay, so in the talk yesterday, the realizations were of principal series type, and it was for Lie algebra of type BOC, if I remember. And so in this case, you'd have an affine Kac-Moody algebra, which you realize using your favorite representation, and you obtain some integrable system. So of course, these two approaches are very intimately related. And in fact, you can go from one to the other. You can start from the action for Chern-Simons theory, perform a Legendre transform to get to go to the Hamiltonian formalism, and after suitable gauge fixing, you end up with a Godin model. Okay. So the motivation for this work was really to try and understand what is the analog of this picture if I replace the affine Godin model by a finite Godin model, which is supposed to describe not integrable field theories, but integrable systems of finite dimension. Okay. So this is sort of the question, what's the finite dimensional analog? And the answer is this picture. So I'm saying finite dimensional analog because, as I said, the Godin model here is based on a finite dimensional Lie algebra now. And the resulting integrable system is a finite dimensional integrable system. Okay, so I'll explain how 3D mixed PF theory on R cross CP1 can be used in the same way as 4D Chern-Simons to construct such Godin models. Okay, so the plan of my talk is this picture. So I'm going to start with reminding you or telling you what the Godin model is. I'll focus on the case of a finite dimensional Lie algebra. And then I'll give you an example of a realization to produce a concrete integrable system out of it. So you should think of the Godin model as sort of a universal integrable model based on a Lie algebra, but then if you realize the Lie algebra in a certain way, you get specific integrable models. And then I'll explain how to get the same model down here from 3D mixed PF theory. Okay, so it's broken down into various steps, so I'll explain these steps after introducing 3D mixed PF theory. Okay, so let me start by recalling what the Godin model is. So the data is, is a finite dimensional semi-simple Lie algebra over the complex numbers. Fix some non-degenerate symmetric bilinear form on the Lie algebra. And then you pick some dual bases with respect to this bilinear form. This is just convenient for describing the Lax matrix. And then you fix a set of mark points on the complex plane. So Z1 up to Zn are complex numbers. And the dynamical variables of the Godin model are essentially just copies of the Lie algebra attached to these mark points. So essentially you take your basis elements IA and you introduce an extra label 1 up to n, which labels the marked point. And these basis elements are attached to that particular marked point. So these are sort of the abstract Lie algebra generators, which you should think of as dynamical variables in the Godin model. So the algebra of observables of the Godin model is symmetric polynomials in this Lie algebra G direct sum n. So it's convenient to package all these dynamical variables into a matrix. Namely, you just take the tensor product with the dual basis element. So in GLN, you should think of this as a matrix. So you can also do this for reductive Lie algebras. In this case, you'd have in GLN, you have a matrix here, and these are just the abstract generators of the Lie algebras at each site, and they're packaged together in the form of a matrix. Okay? So this is sort of like a G-valued dynamical variable for the Godin model. Okay. So the Lie bracket for these dynamical variables is just the Lie bracket for G, but you have n copies of it which mutually commute. So you take the Lie bracket of dynamical variables at site I and site j. If I is not equal to j, you get 0. Otherwise, you just get the Lie bracket at this site. And you can conveniently package these in terms of the G-valued dynamical variable j in the form of this constant Kirillov bracket. So here I've written the bracket as a Poisson bracket because I'm thinking of classical systems. So essentially on linear generators like these ones, on linear observables like these ones, the Lie bracket defines the Poisson bracket, and then you extend it by Leibniz to all other observables. Okay, so this is really a Poisson bracket on the phase space, and it's given in this form. So this will come up later, so it's useful to remember. Here, C12 is just the tensor product of the dual basis elements of the Lie algebra, and I'm always implicitly summing over repeated indices. So the Lax matrix of the Godin model is given by this formal combination of these G-valued variables. So this bracket can again be conveniently rewritten in this nice form, which is just the Lax bracket for the Godin model. So it's the one I mentioned in the first slide, where now the R matrix is this explicit R matrix. Okay. So the advantage of writing the Poisson brackets of the phase space in this form is that it immediately produces a very large family of integrals of motion, which Poisson commutes. So in particular, if you choose adjoint invariant polynomials, P and Q, by which I mean that they're invariant under the adjoint action, like this, then if you evaluate the Lax matrix, you evaluate these polynomials on the Lax matrix at different parameters Z and W, these Poisson commute essentially by virtue of the fact that the Poisson bracket here is a Lie bracket. Okay. So then, to define the Hamiltonian of the Godin model, you just pick a W and you pick a polynomial, which is invariant, and you define the Hamiltonian as this polynomial P applied to the Lax matrix at W. So this just fixes a choice of Hamiltonian, and then by this construction, you get a large family of integrals of motion which mutually commute with each other. Okay. And I should say here, P is applied to the auxiliary space, to the matrix part, and so what you get out of it is a polynomial in the dynamical variables of the Godin model. Okay. So having the Hamiltonian, we can now define time evolution in this model. So it's just Poisson bracket with the Hamiltonian. For any of observable, the time evolution is given in this way. And in particular, the Lax matrix evolves according to the Lax equation, where M here is just this particular matrix, which is related to the Lax matrix L at W. Okay, so just P prime here is just the derivative of the polynomial, which at a point X in the Lie algebra is just a linear map. But by duality of G star with G, you can think of this as a Lie algebra element. So P prime of X is a Lie algebra element. And so this is really just it's a matrix with entries in the symmetric algebra G direct sum n. Okay, so concretely think of GLN. An example of an invariant polynomial is the trace of x to the n, and this is the formula for m in this case. Okay. So now I want to tell you about a specific realization, which is actually a very broad class of realizations, which I'll then be able to reproduce from the 3D BF theory. So to define them, I need to fix some Lie algebra elements u1 up to un. And I'm going to look at the orbits under the adjoint action of these elements in the Lie algebra G. So these are called OUI, the adjoint orbits. And it turns out that these have a very canonical Poisson structure, or symplectic structure. So these are symplectic manifolds, and the product of these is also a symplectic manifold with this concrete Poisson bracket. So U hat is my notation for points on the orbit. So these are just elements you can obtain by conjugation with some G, with some element of G acting on the starting point UI. Okay, so you recognize that this is the same as the Poisson bracket of the abstract generators of the Godin model. So this tells you that you can realize the Godin model concretely by sending the abstract generators Ji, these are the G-valued generators, to these G-valued points in the coadjoint orbit, or in the adjoint orbit. Okay? So concretely, these Lie algebra generators here, they're sent to the coordinates of this point on the phase space in the basis IA. Okay, so these are functions on the product of coadjoint orbits, and they're the images of the linear elements in this symmetric algebra. Okay. So just to summarize, this is basically the three things I want to reproduce from 3D BF theory. So the Lax matrix in this realization is given by this rational function with coefficients which are these adjoint orbits of fixed elements UI. And then this, by construction, satisfies this Lax algebra. And the evolution is given by this Lax equation, where time evolution is with respect to the Hamiltonian I talked about before, which is P of L of W. Okay? So if you can remember these three equations, they'll come up again, and I'll reproduce them from the 3D BF theory. Mm-hmm. Yeah. What is the difference between this and the previous Lax matrix? So this is just realized concretely in terms of group-valued fields, which parameterize, if you like, the adjoint orbit. So you can think of this H like as your dynamical variable of some physical system. Sorry? The algebra generators are the function on the group. So I don't think I understand the question, but so an example of a function on this product of adjoint orbits is just given by the coordinates of these points on the adjoint orbit. So these are the U hat AI. These are functions on the coadjoint orbit, and they happen to satisfy the same relations as these abstract generators. So these are really functions on the adjoint orbits, right? So you can think of this now as classical physical system where you're describing your phase space by functions on the cotangent bundle of on some symplectic manifold. Okay. So this is really functions on a symplectic manifold, but it's a concrete realization of the abstract generators of the Godin model, which were just Lie algebra elements. Right? So you went from abstract elements to functions on some symplectic manifold. Okay. Yeah, just some arbitrary fixed Lie algebra elements. Yeah. Okay. Any other questions? Okay, so now let me turn to the 3D mixed BF theory. So first let me introduce this theory. So it's defined by similar data to the Godin model. So I fix some semi-simple complex Lie group with Lie algebra G, which will be the same as before. And I also have the same bilinear form as before. And the fields of the model are just given by these two fields A and B. So A is just a generic one form. It's a G-valued one form which is smooth on R cross CP1. So it has in particular legs in the three directions dt, dz, and dz bar, where t is the coordinate on R and z, z bar are the coordinates on CP1. On the other hand, B is just a 1-0 form, 1-0 relative to the complex structure on CP1. So what that means is that it just has a leg in the direction dz. Okay? But importantly, you should remember that these are just smooth functions for the moment of all coordinates, just smooth functions valued in the Lie algebra, smooth functions on this space. Okay. So the action is just given as follows. So it's called BF theory because the action is BF. And in other words, you just take the curvature of the one form A, defined in this way, and you just pair it with the 1-0 form B. Okay. So by looking at the action, there's an immediate gauge invariance coming from the fact that B has only a dz component. So in other words, if A has any dz component, it will just drop out from the action. Okay. So I should say here this is the inner product in the Lie algebra, and it's the wedge product of the forms. Okay, this notation. So I'm taking the inner product on the Lie algebra part and the wedge product of forms. So because you're wedging with B, which has only a dz component, any component along dz for the field A drops out. So you can just fix this gauge invariance by just demanding that A has no z component. Okay. So in particular, now we're left with an A field which has these two components, dt and dz bar, and B still has its one component dz. Okay. So a more interesting gauge invariance is the following, which is more recognizable gauge invariance, where A transforms as a connection. It's really a partial connection because you ignore the AZ component. So G can still depend on Z, but you just ignore any Z component which is produced because we can always gauge it away as before. So we just set AZ to 0. So in particular, because A transforms as a connection, the curvature transforms by conjugation. And so if we let B transform by conjugation, then the action is invariant, okay? Because we have an adjoint invariant bilinear form. Okay. So the equations of motion are easy to derive. So for B, it's trivial. You just get the curvature of A. So that's this equation for B. And for A, you find these equations of motion. So the first striking thing you notice is that this looks a lot like the Lax equation for a finite dimensional integrable system. If you identify BZ with the Lax matrix, and M with minus AT. Okay, so it looks like it, but it's far from it for the moment because there's a big problem, which is that if you call this L and this M, then L and M actually depend smoothly on Z and Z bar, whereas you want them to be meromorphic. Okay, so what we should remember, however, is that we're dealing with a gauge theory, and so the hope is that there's some gauge in which we can actually choose L and M to be meromorphic. Okay, so that's the next part. So let's try to gauge fix to make the Lax matrices or the Lax pair meromorphic. So you notice coming back to these equations that there's these AZ bar dependence on the right-hand side. So if we can choose a gauge where AZ bar is 0, then we'll get that AT is holomorphic and BZ is also holomorphic because the right-hand side here will be 0. So this is the idea. We use this gauge fixing condition, which is really the same as the gauge fixing condition used in 4D Chern-Simons theory to produce integrable systems. So you go to this gauge, and then you find that the equations of motion that I didn't focus on before, they just tell you that AT and BZ, these components are just holomorphic. Okay. So there's still a problem, which is that we wanted Lax matrices which are meromorphic in Z, not just holomorphic. So they have no poles in Z. There's no possibility of having poles so far. And the other issue is that L and M, as derived here, they're completely unrelated. So we want M to be built out of L, remember, as some polynomial of the Lax matrix L. But here, L and M are completely unrelated. So these two issues we can fix by introducing some line defects, suitably chosen line defects in the 3D BF theory. Okay, so let me describe these line defects. So essentially, you just modify the action by introducing some terms which are localized on some lines in this R cross CP1 three-dimensional space. So I've drawn here a picture of CP1 just as a plane, and then R as this transverse direction. So what you want to do is modify the action by adding two types of defects. So we call these type A and type B because they depend just on A and B fields. And so these are localized on these lines, which are at the marked points Zi of the Godin model for the type A defects, and at some new point W for the type B defect. Okay? So more precisely, these are exactly the same data as we had in the Godin model, because it will turn out to be producing exactly the Godin model. So these UJs are precisely fixed elements of the Lie algebra G, as we had before for describing the co-adjoint orbits. This H is just a group-valued field on R. It depends only on R because it's living on these defects. And then P is, for the moment, just some polynomial, but it will have to be invariant in a second. Okay? So if we think about gauge invariance, we can, this term is obviously still gauge invariant, but we can promote these two terms to gauge invariant defects. For the second term, we just have to ensure that the polynomial P is adjoint invariant, so that the gauge transformation of the B field is cancelled. So just choose P to be an adjoint invariant polynomial, and then this second term is gauge invariant. And for the first term, you want to just compensate the gauge transformation of the field A by suitably transforming H to cancel off the gauge transformation. So you just choose H to transform by left multiplication by the group valued field G evaluated at the defect. Okay, so this will make this combination gauge invariant, and therefore this second term here gauge invariant. So we have now a gauge theory again. We can look at the equations of motion, and they're now modified precisely by these two terms we added. So the first equation of motion for B is modified by this delta derivative, this Dirac delta function term, which is localized at Z equals W because it comes from this term. Okay, so you can write this as the integral over R cross CP1 times a delta function, and so that's where this delta function comes from. It's in the equations of motion, it's purely localized at Z equals W. And similarly, this equation of motion here is modified by these delta functions at Zj. Okay. So we can now go to the same gauge as before. So again, all these terms with AZ bar disappear, but now we're left with some non-trivial terms on the right-hand side of these two equations. So rather than having L and M now being holomorphic, they're now meromorphic using this property of the delta function. So dz bar of 1 of z minus w is proportional to the delta function. So this gives you that the Lax matrix is now meromorphic with poles at these zj's, and the residues are given by the coefficients of these delta functions. And similarly, the first equation tells you that A, which is minus m, is essentially a rational function with pole at z equals w and coefficient this expression. So that's the expression for m, which we recognize as the Lax pair of the Godin model. So on the equations of motion, we've already reproduced the equations of motion of the Godin model just by introducing these defects in 3D BF theory. Okay, any question? So to really complete the story, we have to now perform a Hamiltonian analysis of 3D BF theory and show that the Poisson brackets of the gauge field, yeah. Yeah. Exactly. So AZ is gone. AZ bar I've set to 0 as well. So all that's left is AT and BZ, and these are the Lax pair of the Godin model. Yeah. Okay. So now let me essentially go back to the start and just start from the action and perform the Hamiltonian analysis of this theory. And the hope is to show that B, which is the Lax matrix, satisfies the correct Poisson bracket, okay, the Lax algebra. So we introduce conjugate momenta for all the fields. The conjugate momentum for the group-valued element Hi at each site is a Lie algebra element. So you can think of this as sort of parametrizing a cotangent bundle for the group element G. So this Xi is like a coordinate on the fiber, and G is a coordinate on the base. So this is the natural conjugate pair describing, or in the Hamiltonian formalism for this group element H. So if you compute these conjugate momentum, you immediately find that they satisfy certain constraints. So for example, the action doesn't depend on the time derivative of AT, so the conjugate momentum has to be 0. And you get these other constraints just from computing the conjugate momenta of these variables. And then you notice that some of them are second class, meaning that their Poisson bracket is invertible. So this means that we can fix them strongly to 0. We want to sort of gauge fix and eliminate all the constraints. We can do this by essentially introducing or replacing the Poisson bracket by the Dirac bracket. So we can fix PZ and CZ strongly to 0 by replacing the Poisson bracket by this modified bracket, which is the Dirac bracket. So I've written it here explicitly, just if you've never seen it before. So these double angle brackets are just given by the pairing on the tensor factor I. So here, for example, there's subscript 2. So I'm pairing the 2 space here with the 2 space there. And then I integrate over CP1. So all these fields depend on Z and Z bar. They don't depend on time because I'm dealing with the Hamiltonian formalism, so I'm at equal time. I'm looking at an equal time slice. And what this here is the inverse of this Poisson bracket. So the point is that this is invertible because it's just the kernel of the identity operator relative to this pairing. And so what's written here is really its inverse, which is just the standard formula for the Dirac bracket, which will allow us to fix these constraints strongly to 0. So it turns out actually that this Poisson bracket, or the Dirac bracket, is the same as the Poisson bracket for all the other fields. So once you fix BZ and PZ, all the remaining fields have just the same Dirac bracket as Poisson bracket. So I'll just continue to denote the Dirac bracket without the star. But to fix the other constraints, it's a bit more involved. So CI you can also fix completely to 0, meaning we're going to restrict to the subspace in the phase space where CI is strictly equal to 0. So this is more involved. I'm just going to outline what's going on. So this constraint is partly first class and partly second class. So the first class part you can extract as by projecting onto the centralizer of the element UI in the Lie algebra G. And by introducing, in fact, any gauge fixing condition for this first class part, you get a total set of second class constraints, which you can then fix strongly to 0 by introducing some Dirac bracket. So it's a lot more involved than the previous case. And what you find in the end is that the Dirac bracket on the fields H, or rather on the combination U hat, which is H, U, H inverse, these are precisely given by this Kostom-Kirillov bracket. Okay, so after gauge fixing the constraint CI, you basically end up with the Kostom-Kirillov bracket for the fields U hat on the reduced phase space. Okay. So we have one constraint remaining, pi t. And so following the Dirac procedure, what we should do is check that it is preserved under time evolution. So the Hamiltonian, after fixing all the other constraints which I talked about, the Hamiltonian just reduces to this expression. So there's this mu hat, which is this combination here, which will be important in a second, paired with t. And then you have this plus what looks like the Godin Hamiltonian, which is promising. So we want the constraint pi t to be preserved under time evolution. So in other words, we want its Poisson bracket with the Hamiltonian to be 0. So that imposes a new constraint, namely that this mu hat here should be 0. Okay, it's a secondary constraint. And as is often the case in this procedure, there's no tertiary constraint. So the algorithm stops here, and there are no more constraints generated from requiring that this is preserved under time evolution. Okay. So in fact, the reason that there's no tertiary constraints is because this mu is actually second class, which means that, first class, meaning that the Poisson bracket with itself is proportional to the constraint mu hat again. So first class really means that it generates some gauge symmetry, and in fact, mu hat generates the gauge symmetry that we had before, which transforms the connection A as a connection and B by conjugation. So we can fix this gauge invariance as we understood in the Lagrangian framework by choosing this gauge fixing condition. And it turns out that indeed mu hat and AZ bar together are second class. So their Poisson bracket is this expression, which you can invert using this rational function here, which you recognize as the R matrix of the Godin model. So in particular, the formula for the Dirac bracket for fixing these two constraints is simply the same formula as before, but now I use the inverse of the Poisson bracket of mu hat with AZ bar. And this double bracket is the same as before. Okay. So now you start to see this R matrix appearing in the Poisson bracket. And what's really nice is that if you now compute the Dirac bracket for the field Bz with itself. So remember, Bz should be the Lax matrix. And if you compute its Dirac bracket with itself, you find precisely the Lax algebra. Okay, and where I emphasize that this R matrix comes from this rational function here, which came from the formula for the Dirac bracket, which involves the inverses of these Poisson brackets. Okay, so we reproduce the Lax algebra. And because we've now fixed mu hat and AZ bar strongly to 0, what this tells us is that, so if we go back to the formula for the Hamiltonian, remember the Hamiltonian is this. So because mu hat is now 0, we're just left with the second term. So that's precisely the Godin Hamiltonian. So on the completely reduced phase space, where everything's been fixed to 0, the Hamiltonian is this one. So that's what induces the dynamics on the reduced phase space, and it's the Godin Hamiltonian as expected. And also because mu hat is 0, if you look at this equation, it's telling you, as before, that Bz is just a meromorphic function with poles at the zj's and residues given by these ui hats. Okay, so that's the same formula as before, just rederived from the... Yeah, exactly. Yeah, because, so I didn't really say here, but these u hats were the same as before. They're the sort of the points on the I-joint orbits, yes. Yeah, but now it's not 3dBF because we've gauge fixed down to basically we've eliminated the CP1 essentially. So we've reduced down to the reduced phase space, which is actually parameterized by these BZ, and so it's actually the product of co-adjoint orbits, right? Because the BZ is really just the same data as these U hats. Yeah. Yeah. So if you're familiar with the Hitchin system, you'll recognize this as the moment map for the Hitchin system. If I identify the Higgs field with Bz and A with the AZ bar component of the gauge field A. And so what mu hat is, setting mu hat to 0 is just setting the moment map to this particular value, which is what you typically do in the Hitchin system when you have defects at the ZIs, when you have ramification points at the ZIs. But you can also, if you replace CP1 in this story by a Riemann surface, you can also fix this to 0 and obtain the Hitchin system out of this construction. Okay. So one last thing is we know that from this bracket we get that the adjoint invariant polynomials of B commute with each other, but we can see this quite nicely from the analysis I just described. So if you pick just generic polynomials P and Q, then because BZ commutes with itself, then the Poisson bracket of the polynomial P of Bz is commuting with the polynomial Q of Bz, just because B commutes with itself. So this is the Poisson bracket. But if you have adjoint invariant polynomials, then because P is adjoint invariant and mu generates the gauge transformation by which Bz transforms by conjugation, this tells you that the Poisson bracket of mu hat with the polynomial P of Bz is 0. That's by adjoint invariant of the polynomial. So it's also true for Q, but what that means is that in this formula for the Dirac bracket, this term is 0 and this term is 0, and that one is 0 because of this fact. So you basically get for free that the Dirac bracket of these two polynomials is 0. So this is the involution property just derived within this Hamiltonian construction. Okay. So let me conclude. So in this talk, I explained to you how by introducing certain line defects in 3dBF theory, namely these particular line defects, you can reproduce the Godin model in the realization where the abstract generators are realized in terms of points on the coadjoint orbit O of uj. But it would be interesting to understand if there are other types of defects you could add to 3dBF theory to produce other realizations of the Godin model, and in particular, it would be nice to understand what is the sort of correspondence between choices of line defects in BF theory and realizations of the Lie algebras G at each site in the Godin model. So this is really a similar question you can ask in 4D Chern-Simons theory about surface defects and realizations of the affine Godin model. Another direction is there are lots of generalizations of the Godin model. In particular, you can increase the order of the singularities in the Lax matrix to have irregular singularities. So these would be reproduced by essentially what you could call thickened line defects, which are sort of line defects where you remember some transversal directions by some epsilon nilpotent parameter. So this has been worked out in 4D Chen-Simon's case in these papers. It would be nice to understand the similar story in this finite dimensional case. What are the analog of the defects we introduce for higher order poles in the lax matrix? You can also have equivariant lax matrices under some group gamma, which could either be the cyclic group or dihedral group. So the lax matrix will then be equivariant in this way. And so again, based on our understanding of how it works in 4D Chen-Simons, it should be that to produce such Godin models, you can start from 3D BF theory, but on some orbifold CP1 quotiented by the action of the group G, gamma. And then there are lots of other generalizations, super Lie algebras, combinations of the above, and so on. Of course, the most interesting direction is for quantization. So the advantage of this 3D BF theory and its relation to the Godin model is that we know a lot about the finite Godin model and its quantization, as opposed to affine Godin models for which we know little about the quantization. So this should be a very useful toy model for understanding how things work when you pass to quantization. So many mathematicians have worked on the quantization of the Godin model, and they've understood that it's related to the representation theory of the affine Kac-Moody algebra, where the affinization here has to do with the spectral parameter, nothing to do with field theory. So the representations of the affine algebra at critical level. Okay, so in particular, all the Godin model Hamiltonians you can obtain from certain singular vectors in the representation of, in the vacuum Verma module of the affine Kac-Moody algebra at critical level. So in fact, classically, 3D BF theory can be obtained as a certain level 0 limit of 3D Chen-Simons. So of course, if you take the naive level 0 limit, you just get 0. If you want to retain some non-trivial information, you can scale the field AZ as 1 over k times BZ, and then that produces BF theory. In the quantum case, when you pass to the quantum case, we expect that the level should go from the 0 level to critical level. So we expect this from the Godin model point of view, and there's also some recent work by Gayotto-Witt and Zhang on where they speculate on the quantization of the Hitchin system, and they argue that critical level Chen-Simons theory in 3D should be related to integrable systems, quantum integrable systems, namely the quantum Godin model, or more generally the quantum Hitchin system. So the quantum version of the picture I've described in this talk should be the following. Okay. And then finally, the original story of Costello from 2013 was about producing lattice models, and it was further expanded on by Costello and Yamazaki. So in particular, among these integrable lattice models, you can produce Heisenberg spin chain, of which we know a limit is the Godin model. So in this talk, I mentioned that the Godin model can be obtained from 3D Chen-Simons theory, and in the quantum case at critical level. So it would be interesting to understand how this diagram commutes, where on this side you basically take the classical limit of the spin chain of Heisenberg to get the Godin model. What's the analogous procedure to go from 4D Chen-Simons here to 3D Chen-Simons, which describes the Godin model? So, and then in particular, in both cases, you have line defects. It would be interesting to understand how these choices of line defects to produce Heisenberg relate to the choices of line defects we've introduced here to produce the Godin model. Thank you.
Thank you, Benoit, for a nice talk. So the talk ended even slightly earlier. We have time for questions. Please, Enrico. Yeah.
Very nice talk. And I want to ask very basic question. If you could reproduce a construction imposing, for example, some periodicity, say substituting the sphere with the cylinder, going like to hyperbolic case, quadratic, and also going to quadratic Poisson brackets, and doing some kind of relativistic deformation of this story with Poisson non-abelian symmetries rather than the usual Lie algebra orbit. If there is some impediment, or maybe you already know, and what you've
obtained in the end. Where do you want to introduce periodicity? And what?
in respect to the z variable, say z variables are not on a sphere but on a cylinder. In a sense.
This is probably related to the orbifold story. If you have these lax matrices which are invariant on the ZT, the action of some cyclic group, here, this. So you pick gamma to be the cyclic group, then you're orbifolding, so you have this periodicity in the Z direction, around the origin. Is that what you're thinking about?
Yes.
So this would produce trigonometric models. In fact, you can also look at equivariance under the action of Z, the integers, which would, in that case, I think, produce, so Godin models with this equivariance would produce trigonometric models, I think. So, but why did you mention quadratic brackets? I think quadratic brackets, as I mentioned in the first slide, you can't really get from 3D BF3, from my understanding.
Quadratic brackets in another direction, you say, kind of relativistic or Poissonly deformation of this procedure.
So maybe, relativistic deformations of trigonometric models. So maybe, I mean, this is related to this slide here, where if you probably take the cyclotomic Godin model, which is equivariant in some way, producing a trigonometric story, this probably has a deformation to quadratic brackets coming from 4D Chern-Simons. So my point, the main punchline is that 4D Chern-Simons can produce finite dimensional integrable systems with quadratic brackets. And if you want models with linear brackets, you should use 3D Chern-Simons or 3D BF theory classically. Okay, so the deformations which go from linear brackets to quadratic brackets in the gauge theory perspective is going from 3D to 4D Chern-Simons. Yeah.
Thank
Can
you.
it be generalized to elliptic case?
Elliptic would be where you, I think, take CP1 to be the torus. Yeah.
Well, it's quite possible.
Yeah, you can do this as well. So, in fact, in this story, you can do the same thing for any Riemann surface, and you get Hitchin systems. And Hitchin systems on tori are elliptic systems.
So, further?
Thanks for the nice talk. It seems transparent at the level of the equations of motion that you land on this, these Godin models. You get this lax matrix. But at the level of the Poisson brackets, can you give some intuition for why this should happen? I mean, why should you land on the right Poisson brackets?
Well, so the strategy is basically just fix all the constraints as you can, and then when you encounter a gauge invariance generated here by this constraint, you know what this gauge invariance generates in the Lagrangian framework, and you knew how to gauge fix it by imposing AZ bar equal to 0. So it's just following the same story, but in the Hamiltonian language. I'm saying it's completely parallel. So all these choices were guided by what happened so clearly in the Lagrangian framework. So in the Lagrangian framework, when you look at the equations of motion, it's immediate what to do, right? But in the Hamiltonian framework, it's a bit more involved, but it's really the same story. If you're familiar with this kind of Hamiltonian with constraints, it's quite natural to do all this. And the choices which you have to make are sort of guided by the choices you had in the Lagrangian framework. Also, we first worked out the case of the affine Godin model where things were harder, and this was easier to work out. I mean, we knew what to do basically because we already worked out the 4D version. Does that answer your question?
Yeah, okay, thanks very much.
There exist various dualities for Godin models, for example, relating GLN on K sites and GLK on N sites, or some quantum classical or spectral dualities. Can you see or maybe derive them from the other side of the correspondence, from Chern-Simons?
Yeah, so I mean, this is a very good question. I don't know. It would first require quantizing because I don't know of many classical dualities between classical Godin models. Maybe bispectral dualities you can see, but these require very specific representations by rank 1 matrices, and so you'd need to realize these realizations by choosing suitable defects in the 3D BF theory. So yeah, you'd need to find suitable line defects to produce the realizations for that context. Yeah. But I mean, I think apart from bispectral duality, which can happen between two classical Godin models, I don't know of any other dualities at the classical level. So you'd have to first understand quantum Godin models from 3D Chern-Simons. Yeah.
Also, another small question. In principle, you could derive Gaden by taking a limit of the spin chain for which the correspondence was known.
Yeah.
But instead, you found it easier to derive it from scratch, right?
Yeah. Yeah, so I mean, this is the last slide. And it would be nice to understand how to close this diagram, to get sort of a limit on this side. You see, this is the H-bar limit where you retain only the information about the classical R matrix. What's the corresponding H-bar limit in this side? It's not obvious. Yeah.
Sorry, Benoit. Hello? Yeah. One more question. When you talk about this 4D realization R2CP1, I'm just wondering if you know, there is probably also this realization in terms of the moment map for the Hitchin connection.
Yeah, yeah.
And I know that people are able to reduce this problem to the ramification problem, the ramification cycles, which is equivalent to the development quantization scheme. I don't know if you have thought it can be this a universal prescription for constructing quantization schemes, at least for this class of models.
So I don't know, but it sounds interesting because the moment map in the Hitchin system appears naturally in this story as the so fixing mu hat to 0, as I said, is really just the same thing as fixing the moment map of the Hitchin system to this level. In the Hitchin system, you would fix it to 0 if you don't care about introducing ramification points. So on high genius Riemann surfaces, you can fix this to 0, and you'd get interesting Hitchin systems out of it. But so I mean, you could talk about it afterwards. Sounds interesting, but I don't know what. Mm-hmm.
Hi, thanks for the nice talk. Maybe a naive question, but another way to generate many integrable systems is from Einstein's equations. And in 3D, if you had, for example, Einstein-Weil spaces, which are sort of spaces with conformal metric and a connection, do you have an expectation what kind of Hamiltonian systems arise from these equations?
So I'm not too familiar with this construction, but I think I know what you're referring to. So I don't know how it would relate to the Godin model and to these 3DBF theories. But, I mean, maybe you can tell me afterwards.
Okay, okay,
yeah.
thanks.
Okay.
Okay. If there are no more questions, let's thank Benoit again. The next talk. Okay. Our next talk will be given by David Way from Queen Mary, University of London, and it will be about segmented strings in IGST. So, please. So I will show you.
Can you hear me?
Yeah. So you have 45 minutes, and I will show you the fingers.
Okay, great.
Minutes will be left, 5 or 10. Please.
Hi, thanks very much for the invitation. I'm very happy to be here in Budapest. I graduated from this university. Very happy to be back after 20 years. Today I'm going to be talking about segmented strings in ADS3, three-dimensional de Sitter space. And first, I think I have to explain to you why I want to talk about this topic. Okay, so I guess very unusually, I'm going to start from the bottom of the slide. Motivation for studying strings in ADS. At this conference, maybe I should not even have this slide. Of course, one huge motivation comes from studying the ADS-CFT correspondence. ADS-CFT in the planar limit, you naturally end up with strings in a fixed ADS background. Okay, you can also think about applications of ADS-CFT if you're like more condensed matter oriented, or if you want to compute Wilson line scattering amplitudes, studying surfaces in ADS also appear. Now, my personal motivation comes from this sentence here. I'm interested in quantum gravity, and I like to understand it. For that, I first want to study toy models for quantum gravity. So it might be worthwhile going down in dimensions, so down to 2 dimensions. Einstein gravity in 2 dimensions is trivial. You can build other models like the Joukhiv-Teitelbaum gravity theory, which has been very popular in the recent years. It provides a low energy sector of the SYK, the Slajdev-Kitaev model for ADS2. Okay, unfortunately, it does not have local degrees of freedom, so you might want to have a system which does have local degrees of freedom. And the string worldsheet is such a model. Okay, what does it have to do with gravity? My motivation for studying the string came from a series of papers by Shanker and Stanford, where they studied chaos, how chaos appears in ADS-CFT. This is the system that I'm not going to explain now. The bottom line is that they studied out-of-time order correlation functions, 4-point functions. These are hard to compute, very hard to measure, but from them you can read off the Lyapunov exponent, this lambda L here, and that's just a number that you can compute. A few years later, Maldaceno, Shanker, and Stanford found a universal bound, upper bound on the Lyapunov exponent, this 2 pi t. There's some h bar in the denominator. Okay, and Shanker and Stanford showed that, and collaborators, they showed that black holes in ADS-CFT saturate this bound. So later, Kitaev showed that the SYK model also saturates this bound. That's what started this mini revolution in 2015. Okay, in 2017, with Jan de Boer, Eva Labres, and Juan Pedraza, we showed that the string worldsheet also saturates this bound. So in that sense, it is similar to Einstein gravity. It has to do with the phase shift when 2 waves cross on the worldsheet. Or you can also look at, in gravity theory, you can look at gravitational shock waves, and you end up with the same phase shift for some reason that nobody understands. Okay, so that's the motivation, but this is all still very complicated, as you know, quantizing the string in ADS, et cetera, et cetera. So what I'm going to do in this talk is I'm going to discretize the string. Okay, so here's the plan for today. First, I'm going to tell you how to discretize the string, what segmented strings are, and then I'm going to show you a few examples. Animations, I wanted this last talk to be fun. Not that the previous talks were not fun. And then this is an integrability conference, so I'm going to, after that, compute the spectral curve in 2 different ways, just to have even more fun. And then after that, I'm going to discuss the simplest example, which turns out to be a closed string consisting of 4 segments. It's going to be still quite complicated, as you'll see. Okay, everybody happy with this plan? Okay, so here is what segmented strings are. We like to construct segmented strings from straight pieces. Think of piecewise linear strings in flat space. Okay, so here's a straight string. There is a normal vector, which is constant, right? So this is what we'd like to see. So how do we put this in the language of mathematics? ADS3, you can embed that into R2, 2, this ambient space as a hyperboloid locally. So it's a 4-dimensional linear space. You need 3 vectors, this embedding vector y, and then you can take derivatives, light cone directions on the worldsheet. So you got 3 vectors, and there is a 4th perpendicular vector to it, which is your normal vector. Okay, so this normal vector is an element of R2, 2. It does not only describe the direction, the orientation of the string. It also tells you what the transverse velocity of the string is, and also the shift, so where it is in the transverse direction. So this is why I work in ADS3 as opposed to 3-dimensional Minkowski, because you can sort of encapsulate all this information in a nice and covariant way. Okay, so the idea now from 2015 is to glue a big segmented string from pieces which have constant normal vectors. Okay, so I posted this paper 7 years ago, and surprisingly, same place at the same time, Gupser and collaborators also had the same idea this happens. Okay, so how do we describe a string segment with a constant normal vector? Okay, so here is a picture that I'm very proud of ADS3. And this is the global ADS time direction. And the simplest string embedding is here in green. So it just connects to antiporal points on the boundary of ADS, right? And in these coordinates, it's static embedding. The orange slices are the boundaries of the Poincare patch. On the Poincare patch, so here's the boundary. This is the z direction, the radial direction. This green worldsheet looks like, at a given time, like a semicircle, which sort of comes from infinity, shrinks to a minimal size, and then starts expanding again. So that's what it looks like. And you have pictures here how the quarks behave, the string endpoints behave on the boundary. Okay, so this is our elementary string segment. And we'd like to connect two of these. Okay, so how do we do that? So if you just arbitrarily connect two segments, now here I have pictures of the Poincare patch. The problem is that you're going to generate bits of the string which move with the speed of light. So that's not good because this has an infinite energy here. So we don't allow that. So there has to be a constraint for adjacent normal vectors, which turns out that the two adjacent normal vectors, so for the normal vector for this guy and the normal vector for this guy, these have to multiply to 1. Okay, so that's the rule. And this also implies that this kink here moves with the speed of light. This is, you can understand why that is necessary. It's because if it was any slower than that, you could go to a rest frame locally. But then, obviously, because of the string tension, this could not stay piecewise linear because there is like the string does break. Okay, so all the kinks in this talk will move with the speed of light. But they can collide, right? There could be a left-moving kink on the string, a right-moving kink on the string. So eventually, they're going to collide, and you have to handle the situation. What happens when they do collide? So here is a simple, this is really high school algebra. You can go to a frame, so here's a string. You can go to a frame where this line, this string segment is static. This is also static. And this middle one moves upwards with some velocity v, which obviously has to be less than 1. And eventually, these two kinks, they will collide up here. So you can convince yourself that the only thing that can happen is that v goes to minus v after the collision. So there's sort of a time reversal symmetry here. And after the collision, the string segment starts to move downwards. And you can look at this from the point of view of the normal vectors, how the normal vector A corresponding to this middle segment changes. And there is this reflection formula, which kind of tells you what happens. So you have to reflect this normal vector A on like sort of the average of the other two normal vectors. Okay, so let's see how this works in practice. So I'm going to show you a few animations, and then we get back to integrability. Okay, so here you see 3 segments on the Poincare patch. This is segment 1. This is a middle segment here, segment number 3. And after the kinks collide, you see the normal vector changes, and this middle bit leaves this dashed line here. Okay. Let's see the next one. Okay, you can do some crazy things in global ADS. You can generate lots of kinks, and at the end of the talk, you'll be able to compute the spectral curve for these guys. Well, closed versions of it. You can also, so as it turns out, segmented strings can approximate any smooth string to arbitrary accuracy. So this is a dense set in the space of string solutions in ADS. So here I'm approximating this dashed line, which is given by some elliptic integral. So there's just a string hanging from the boundary of ADS, and I'm approximating it with this complicated string, which contains lots of kinks moving with the speed of light. So that sounds a bit silly. Why do I do that? It's because after that I can do this. So this, now you don't see the individual segments. There are like 500 segments in this animation. So you can perturb one of the endpoints. After the quench, there's a large wave that's created, and you can study things like wave turbulence using this integrable model. Okay, so I cut off the animation at some time, but this can go on for an arbitrary time because it's an exact solution to the number go-to string in ADS3. All right, so let me go back to the talk if I can find it. Thanks. Okay, so how did I do this, especially the last animation? I have to go back to this. Unfortunately, if you try to just implement this reflection formula, this kind of exponentially increases the tiniest numerical errors. So it's not good because computers store real numbers as rational numbers. And after a few hundred reflections, those tiny errors get blown up, and you end up with a mess. So there, I found a different description, which I'm going to tell you about now. Okay, so this brings us to this topic of celestial variables. This is all related to Andy Strominger's story, except they work in Minkowski spacetime, and I work in R2,2. Okay, so maybe the letters are tiny, but I'm just gonna tell you the main story here. So let's look at the wordsheet. So how do we quantize? How do we discretize the string? Here's a wordsheet, and these lines here are the kink word lines. So as I told you, they move with the speed of light, so these are 45-degree angles. Okay, so the vertices are this V0, V1, etc. These are all in points in R2,2. Okay, so you can subtract them from each other. It's a linear space, so I can just generate these P vectors. And then, you know, if you rotate these by 90 degrees, you can think of this diagram as a Feynman diagram. Okay, so what is the action of the string? Well, the action is just the area of this diamond. So for dimensional analysis, this area can only depend on the ratio of these two Mandelstam variables that you can build from these P difference vectors. And in some nice and symmetrical case, you can actually do the integration and figure out that the function is just log of U over S squared. Okay, so that's the area. Now these P's, these kink velocity vectors are null vectors in R2,2 because the kinks move with the speed of light. So now you go to the spinor helicity formalism, and you build these P vectors as a product of two spinors. These are two component spinors, and they are real because we are in R2,2. Okay, so in terms of these lambda tilde vectors, you can write down this area, and using the fact that these four lines have to close, momentum conservation, you can eliminate the lambda tildes from the formula, and you end up with this kind of cross ratio looking thing in terms of the lambda variables. Now you see that lambda 1 appears upstairs and also downstairs, and same for the others. So you can multiply the spinors by a number, and that drops out. So in fact, only the angle or the ratio of the two spinor components will matter. Let's call them celestial variables. So you have the two component spinor, and I just take the ratio of the two components. And I'm going to call these A. numbers, celestial variables. In terms of the original difference vector, it's a formula like this. Okay? If you're familiar with the celestial sphere story, then there's an I in that story here in front of P2. But in this talk, everything is real, except for perhaps the spectral parameter. Okay, so in terms of these A numbers, you do get a cross ratio. So that is the area of the string worldsheet for this patch. Okay, just to summarize, we went from the vertices, we computed these difference vectors, we decomposed them into a product of two spinors, and the spinor component ratios are the celestial variables. And these A numbers sit on the edges, the kink word lines. So one kink word line, one celestial variable. So what's the next step? Well, we add up the areas of all the patches. So you compute the total action. You compute the total action, you have the action, you can derive the equation of motion for these A variables, the celestial variables. And this is what you get. Okay, so here is the worksheet again with lots of patches. And I put here these white and black boxes so that you can see that they form a square lattice. Okay, and when you compute the equation of motion for the celestial variables, this is what you get. It's a known integrable model. Oops. It's a nonlinear model, so not entirely trivial. Okay, so what if you have all these celestial variables, you solve the equation of motion. How do you reconstruct the string embedding? Well, it's not too complicated. So here is the artist's impression of a worksheet. And there are some kink lines here denoted by these black lines. And I sort of unwrap it, and I show it here on the right-hand side as well. So if the enemy gives you these two rows of celestial variables, this guy here, this, that, etc., and the enemy also gives you the p point, you can compute the normal vector of this adjacent ADS2 patch using some complicated, not too complicated reflection matrix. So remember, P is a vertex in R2, 2. You multiply, you apply this 4x4 matrix on it, and you get another 4 vector, which is going to be your normal vector. And then you can do this procedure again from N1, this normal vector, you can compute this Q point using these two celestial variables. And so on, you can continue the procedure, and you recover the entire string embedding. Okay, so surprisingly, or maybe not too surprisingly, just by knowing these celestial variables, you can reconstruct the entire string embedding up to a global SL2 transformation. In the smooth limit, these two, the black dots and the white dots, they become two different smooth fields on the string worldsheet. All right, so now we know how to generate those animations I showed you. Let's talk about something else. So I'm going to tell you a simple brute force way how to compute the spectral curve. And then I'm going to tell you it in a different, more exciting way. Okay, so using the Pohlmeier reduction, you can massage the equation of motion, and then you end up with the generalized Hinge-Gordon equation, which is written here. Okay, for this equation, the flat connection is known. I just copied some equations from this paper by Alday and Maldacena, 2009. And you define an auxiliary linear problem. So this psi is a two-component spinor. And if you solve this spinor, these spinor equations, from the solutions you can reconstruct the string embedding. So in general, it's very hard to solve these equations, of course. But we are dealing with segmented strings, and the elementary segments are very simple, like ADS2 patches, basically. So you can, in fact, you can solve these equations. So here's one patch bounded by the kink word lines. And you can solve the spinor equation here. And you'd like to connect it to some other spinor solutions and build the global spinor frame. Okay, so what it turns out that you have to connect it to another spinor solution, which is is valid in the vertex region. I blew up this dot here, which is now this orange region. That's the kink. That's the vertex region where the embedding function does not change, but the normal vector changes. Okay, so you can also solve a similar equation here. You get the spinor solution here in the orange region. You have it in the ADS2 region. And then using some matched asymptotic expansion, you can connect the two solutions, and you can figure out what the LOX matrix is. So you end up with this 2x2 SL2 LOX matrix, and zeta here is the spectral parameter. You can either do this, or you can just look at the book by Suris and discover a very similar matrix. All right, so from these LOX matrices, you can build the monodromy for a closed string. Just basically multiply these matrices and their inverses. And in every matrix, there are two celestial variables which enter. So you can actually write down the spectral curve in terms of these celestial variables completely explicitly. Now that's not all of the story, because these celestial variables are not completely arbitrary. There are some constraints, because if the enemy just gives you 2n celestial variables, then the string won't close. So you want to avoid this kind of situation. There is a constraint, a global constraint, which forces the string to close. And that turns out that it's equivalent to this constraint. Some special point, this omega monodromy matrix has to be trivial. Okay, so this gives 3 real constraints on the celestial variables. All right, so that's the sort of brute force way. And now here's the exciting way of computing the spectral curve. And it's especially exciting to me because it connects with my old work on brain tilings from 2005 and 6. Okay, raise your hand if you know what a brain tiling is. Oh, 1%. Excellent. 2. Good. Okay, so what is brain tiling? It's a doubly periodic bipartite graph. So the fundamental domain is indicated here by this red rectangle. So the tiling, you can think of it as a planar graph drawn on the surface of a torus. Okay, so we used these objects back in 2005 with Ami Hanani, Seba Franco, and others to encode the Lagrangian of n=1 supersymmetric gauge theories in 4 dimensions. The dual graph, the graph theoretical dual, is the quiver of the theory. And interestingly, the tiling also encodes the terms in the superpotential. So these black and white dots are going to be terms in the superpotential. And this is also related to the story of these people on on-shell diagrams, right? Except that in this case, the tiling is, it's on a genus 1 surface, not planar. Now, it's often said that the best invariant of a graph is the graph itself. So that's true for generic graphs. But for this particular planar doubly periodic graphs, you can in fact find an invariant object. And it's basically you take the adjacency matrix of the graph, and you compute the determinant. So you get some polynomial in 2 variables, and the Newton polygon is drawn here on the right-hand side. Now, there are transformations you can apply on the tiling. So this one is a famous one. This has at least 10 different names. urban renewal, spider move, Plasnikov move, square move. We call it a Seiberg duality in the context of n=1 theories, which is an infrared duality. And there is another move where you eliminate valence 2 vertices. And the invariant object it remains the same. So the Newton polygon does not change. Here's a little bit more concretely, the calculation for this particular tiling. So you assign weights to the edges which cross the boundary of your fundamental domain. So x inverse depending on the orientation, and y here which crosses the vertical boundary. And you build the adjacency matrix, which in this context is called the Castellane matrix. Okay, so the rows and the columns are labeled by the black and white vertices. So there are 6 vertices, 3 black, 3 white, so this is a 3 by 3 matrix. And you see, for instance, the 1, 3 component is 0 because the white 1 is not connected to black 3. But the white 1 is connected to black 2, so I put a +1 here. There are also some signs that I'm not going to explain. Okay, so that's the Castellane matrix. You compute the determinant, you get a Laurent polynomial in 2 variables, which then gives you this Newton polygon. Interestingly, you can go from this Newton polygon back to the tiling. I mean, at some point you take a determinant, so it's a bit unusual that you can do that. I found a very nice graphical way to do this back in 2005 with Ami Hanani. You don't get the tiling uniquely, you get it up to these transformations that I showed you. All right, so about 10 years ago, Gončarov and Kenyon told us that there is a corresponding quantum integrable model to almost every tiling, and the dynamical variables are oriented edge loops in the tiling. So for instance, this edge loop here. Or you can go around the face, so that's another edge loop, and that will be a dynamical variable in your system. So these face edge loops are denoted by Fi. This form a basis for all the dynamical variables. And in the Gončarov and Kenyon story, they satisfy quadratic Poisson brackets. This can be quantized. Unfortunately for us, for the string sigma model, we don't get quadratic Poisson brackets. For the string in ADS3, I'm not going to talk about that, but these are quartic brackets that we are interested in. But no matter, the equations of motion are the same, so we can try to embed the motion of the segmented string into these systems. So how do we do that? So I like to look at I want you to look at the worksheet again. So here are the kink lines. This is the tau direction. This is the sigma direction on the worksheet. You can think of sigma as being a compact direction, so we study a closed string. And think of it as an on-shell diagram. So here where 2 kinks collide, like, oh, the mouse keeps jumping. This point here, or that point, or this point, you can think of that as a sort of composite vertex. So blow it up. So that's what I did here in the middle figure. I added these 3-level diagrams, these squares, and you can imagine that they are growing now. So you collapse these 2 black dots, these 2 white dots, these 2 and these 2, etc. So we end up with a square lattice. Okay, it's periodic in the sigma direction, and it's not periodic in the tau direction. This is not the brane tiling. This is still just an on-shell diagram. To get to the brane tiling, well, it already suggests that you are going to end up with a square lattice. So instead of tau, you want to pick an auxiliary direction. And this is what I'm showing you on the right-hand side. So the horizontal axis is still related to the sigma direction on the string. So you go around the string. That's this horizontal direction. But this vertical direction this is going to be always 2 square tall. This is the auxiliary direction of your spectral curve. Okay, so this is the brain tiling. For a segmented string with n segments, it's a 2 by n square lattice, and doubly periodic. Okay, so how is this related? And I can just color these faces with 2 different gray colors, because these 2 face variables, dynamical variables, sort of mean different things. So how are these dynamical variables related to the celestial variables that I talked about? Well, it turns out that they can be given by cross ratios. So these p's especially are just simple cross ratios of nearby celestial variables on the worksheet. The indices don't look at the indices. It's not important. The Q variables are slightly more complicated cross ratios. What's important is that these are Möbius invariant. So sort of the isometry group of IGST is gone now if you look at the brain tiling. Now you can start to perform cluster transformations. These are the urban renewal transformations, and you can figure out how they act on the dynamical variables P and Q. And this is what you get. So you see that the P and Q variables form a Y system. And then you can check explicitly that these are compatible or equivalent to the original equation of motion for the celestial variables. Okay, so we managed to embed the motion of the segmented string into the cluster transformation dynamics of a brain tiling, this particular brain tiling. And it's very easy to compute the spectral curve because you're going to want to just compute the determinant of the adjacency matrix, the Castellane matrix, and you have the spectral curve in terms of your celestial variables or these P and Q variables. All right, so let's have a look at the simplest case. I don't have an animation for this. You can just sort of move your head left and right. So this is one of the, these are snapshots of the string, and it sort of just oscillates between these 2 positions. This string is characterized by 2 numbers, the length of this line here and the length of that line here. Yes? Which argument?
Control.
Yes.
On the integrable system. Can I see it as having always a dual quiver behind you kind of?
I mean, depends on what you want to do with the dual quiver.
Yeah, probably such that the quiver is
Yeah, I did not think about that. Yeah. All right, so just back to this picture. So this string is characterized by 2 numbers, these 2 lengths. And if I were to set this length to 0, that's a very special case, then you just have basically 2 endpoints moving on a subspace like that, connected by a string. That's the simplest folded string, and it only has longitudinal degree of freedom. Okay, so here's the calculation. It is really very simple. Here's a picture of the string again, and here's the worksheet. And these 2 dashed lines are identified. So this is the tau direction, that's sigma. And this P point is the same as that P point. And on a generic time slice, you have 4 kinks or 4 string segments. And on the right-hand side, you see the brain tiling. It has 8 squares. And now you can compute the Castellane matrix. So you can compute the spectral curve in 2 different ways. You can either use those omega 2 by 2 matrices, Lux matrices, and multiply them. and then build a spectral curve like that, or you can just compute the determinant of the Castellani matrix, and you get the same thing. You get this result where x and y are the two weights when you cross the edges, or the boundaries, and delta is the space-time energy of the string. Okay, so delta is the space-time energy of the string, which is related to the two lengths characterizing the string. So they do not appear separately. This also means that from the spectral curve, you cannot reconstruct the string embedding completely uniquely because you've lost information. Okay, so you have x and y, that's your spectral curve, but I'm now going to define some other spectral parameters. In fact, there are 4 different spectral parameters on this slide. I'm sorry about that. There is this zeta, and I think zeta squared is x, and x is related to the Zhukovsky x like this, and then you can define this u spectral parameter from the Zhukovsky x via this formula. And finally, I rewrite y as e to the p. And then we go to the thesis of the previous speaker, and you learn that p and u are canonically conjugate variables. So in terms of p and u, this is your spectral curve. It's very simple. And I defined here this g, some coupling constant. Okay, what else do I want to tell you about this? You can also express delta, the energy, from this equation. And this is what you get. So if you're familiar with the Reisenauer-Schneider theory, you get something that looks like that, except you don't have the Weierstrass P function in here. You have something simple. And this H is not, it does not generate the Poincare algebra. It's part of the an SL2 algebra that's more appropriate for ADS2 or ADS3. Okay, so here, this is now where I would turn to quantization. Unfortunately, that's work in progress. So this is my last slide. So I can spend 4 minutes on this slide. It needs more than 4 minutes, I can tell you that. So here is the spectral curve again. And as I told you, the spectral curve does not depend on this squashing parameter. You can compress the string completely, and you end up with 2 endpoints connected by a string. So you squash the string, and you can also go to the flat space limit. Who cares about ADS3? Go to the flat space limit, so you really just have 2 sort of quarks connected by a string. And in this limit, the quantization probably should be given by the 't Hooft equation. So the 't Hooft equation, the 't Hooft model, well, if you've never seen this paper, you should read it today. It describes meson band states in planar 2-dimensional QCD. So this phi of x is the wave function, and x is the momentum fraction, the Bjorken x. So this p is the capital P is the total momentum of the 2 quarks. So you boost the 2 quark system, and p1 is the momentum of one of the quarks. Okay, so x is just the ratio. And the other quark has momentum fraction 1 minus x. Okay, so then this integral equation describes the wave function. Alpha 1 and alpha 2 are some renormalized, or the renormalized mass squared numbers here. You can set them to 0 here for the purposes of this talk. And now you can switch to rapidity coordinates, this theta, given by this expression, and do a Fourier transformation. And then you end up with some 5 new function, still an integral equation, but you can turn that into a difference equation. So a simpler version was already in this paper by Brouwer, Spence, and Weiss at the end of the 70s. But this particular equation I've seen in this paper by Fadyev, Lukyanov, and Zamoachkov in 2009. So they end up with this equation. And looks complicated. What does it have to do with this equation, or classical spectral curve? Well, since the system is very simple, you can also just compute the Hamiltonian and everything by directly looking at a folded string in ADS3. And if you know a little bit about the Reisenauer-Schneider model, you can figure out some canonical transformation between this P and U variable and those more natural physical variables, like the quark locations in ADS3. So you can actually relate this U, you can figure out the configuration space exactly. And it turns out that this region, which in some other models is the Joukowsky cut, this is not part of the configuration space. So only U larger than 2G or U less than minus 2G is part of your configuration space. So you might want to cut this out. Okay, so you can define some U tilde variable where you sort of take this middle region and you cut it out. And then you glue your space, your real line, U line back together again. So that's what this U tilde is. And in terms of this U tilde, you get a weird looking equation, which obviously has an absolute value in it. So I'm just gonna let you now compare this equation and that equation, and compare this tanh nu over nu to this 1 over U tilde absolute value. So maybe you can think of the Toft equation as a very simple quantum spectral curve, which works slightly differently because you cut out a region. Okay, I think my time is up, so I'm just gonna leave you with this summary slide. So we studied a bosonic string in ADS3, and using exact discretization, we reduced it to a model with a finite number of degrees of freedom. And we computed the spectral curve using brain timing technology and some other brute force way as well. And there are some questions, how to quantize these objects. Well, in the flat space limit, this is what you should get from the previous slide. This would be super useful if you were to really study quantum gravity. Now, you might run into difficulties, so you might just want to go to ADS5 cross S5 instead. So how to generalize this to ADS5 cross S5 is still unknown. And the final question is, if you really think about the string worldsheet as a model for gravity, the question is, does it have a holographic dual, some kind of 0+1 dimensional theory, maybe a matrix model? And again, I don't know the answer to this. Thank you.
Thanks a lot for a very nice talk, David. Please, questions? Kola?
Hello, thanks for the nice talk. Can you have a version of this on S3 rather than an ADS3?
A version on?
For string on S3 rather than on ADS3.
S3?
Yes.
Excellent question. I tried to do that. I failed. I suspect it should work in some ways, but I don't yet know how. I think it's easier to generalize it to ADSN. S, I don't know. The problem with exact discretization is that there is no algorithm to do that, right? So it's easy to go to the smooth version from the discrete version, but not vice versa.
More questions? I wanted to ask you something. So you get something like R matrix here, yes? For could it
I
be
only told you
called-
about a system with 1 degree of freedom, like at the end. The R matrix, I don't know. I have not looked at it yet.
But if you have,
I don't know if it's a quantum integrable model
if
or
you
not.
have a few degrees of freedom,
That's what you want, yes.
do you feel it's integrable also? So there is no clue yet what kind of
It's unclear. Classically
which
integrable.
integral model you can map it. Sounds, many elements sound very, very familiar to integrability.
Classically, it's integrable, but quantum story, I am not sure.
No, okay, even classically, I mean. Okay, thank you. So, if there are no more questions, let's thank again David. Let me say a few words at the closure. Since I didn't give any speech on the boat, I will take this opportunity to say a few words. It will be very short. That it's I calculated it. Now it's the 18th edition of our IGST conference, essentially. So it's already close to a span of one generation of physicists, maybe a little bit less, but it's approaching. And I'm so happy to see that new people come to the subject, many new faces, young faces, essentially. And that it means that our subject is alive and doing still very well. And it's not only due to the quality of your research, but it's also due to some people who decided to spend, not to waste, of course, but to sacrifice a few months of their life to organize these meetings, which is the most essential event in our science. And over the years, there have been many great meetings, and this one, of course, is another one which was excellently organized, and really no reproach, only good words can be said about this organization. And let's thank Zoli and the whole team of organizers for this great conference. Thank you very much. And just the last thing to add, that of course it would be good if more people volunteered from various countries, various laboratories to do these conferences. It would be good to have, I mean, the choice in the next years. So you are welcome to volunteer. Thank you very much. I give the word to Zoli.
So I asked actually Gigina to make a scientific summary of this workshop. So please, Gigina.
I suppose this is the... Yeah, so I have the privilege to make a few concluding remarks about the conference. So, of course, we would like to thank the organizers for this perfectly organized conference. My friends reminded me that the ADS-CFT integrability activity is already 20 years old. So in 2002, there were two founding papers. We had a controversy which one is more had more impact on the activity. So you can contribute to the discussion. It looks like it's a competition between Princeton and Uppsala. So the activity is already, so it's a venerable age for this community. I wanted to find a picture from the first conference with the founding fathers, but what I found the closest to this is that one. So it's called the chain of authority, and you see that it looks like a spin chain in the L state. So just coming back to the place and the time, the present place and time, I think the two keywords which were most frequently appearing in the talks were chain and bridge. So I think, oh, sorry, I think this is the object which puts together the two concepts, and to recycle the citation of that Florian used in his talk, we can think this as a bridge from beauty to the truth. So this would be, if you look for the chain bridge on a picture of chain bridge on Wikipedia, this is what you get. The truth is more like this, so it's work in progress. This is what I got from the boat, from our nice boat trip. So yeah, that's our journey from beauty to truth. So to say a few things about the scientific content of the conference, as usual, the main subject of study of the work presented here is the N=4 Superior-Mills theory, which can be considered as the mother theory or the queen of the theories that we are studying. There are also the little sisters and daughters, ABJM, ADS3, CFE2. The deformation N=2 superconformal theory or fishnet theories. So these are all deformations of the mother theory. So we have seen part of the talks were about the core objects of this theory, so the amplitudes, form factors, correlation functions. We have seen all this sophisticated technology that was developed during all these years, getting into sophisticated mathematical objects, polylogarithm, symbols, cluster algebras, so on. So we have seen the hexagon, pentagons used to compute these objects. So we have seen a few talks about defects and cross-cap. The spectrum of, in fact, this is the rebel daughter of the field, which still resists characterization. So we have seen a few more contribution about this theory, also deformations and integrability, and then there are the bridges to more general aspects of integrability, integrability to apply to condensed matter, and so on. So in the next slides, I will remind a little bit more in detail the contributions that we had in all these different directions. So the core field of research in N=4 Superior-Mills, or the deformations, or the other theories which are correspond to gauge string duals. We have seen, so the very interesting new contributions about amplitudes in fishnet theories, connections to Calabi-Yau manifolds, and another connection to string theory through these objects. We have seen, this was presented by Florian. We have seen some nice advances in the resummation of amplitude-headroom in the talk of Jaroslav Trinka. New results on Virasoro-Shapiro string amplitudes in ADS space by Fernando Aldai. We have seen new aspects of integrability in the bootstrap for the form factors, advanced results for up to 8 loops, duality between form factors and gluon amplitudes in the talk of Matthias Wilhelm. We had a new conjecture for the form of the 3-point function in terms of quantum spectral curve data in the talk of Benjamin. Then higher point correlators, multiple OPE expansions, light-like limit, links to Toda equations in the talk of Enrico Libucci. Also correlation functions of determinant operators in fishnet theory by Eduardo Vescovi. And then, very similar objects, but in theories with defects or deformation, deformed theories, or like in the talk of Kostia Zarembo about D-branes and one-point functions in ABJM. And also we have seen how to compute the overlaps between these matrix product states and arbitrary beta states. Transformation formula for the Godin superdeterminants. In the talk of Shota, we have learned about n equals 4 super Young Mills on RP4 and crosscaps and integrability of crosscaps and long-range entanglement in spin chains. So then we had this nice series of talks about ADS3 CFT2 theory with a new results on mirror TBA for ADS3 CFT2, a new proposal for the dressing phase, and some insights about interaction of massless and massive modes that were shown by Alessandro. Relatedly, we had a quantum spectral curve proposal construction for this theory. Sorry, there is this is copy and paste. Yeah, so it's it's in the talk of Andrea Cavaglia, and as we have just learned, there is a version of discretized strings in ADS3 with a computation of the spectral curve of the string in this space. And then on the deformations, deformed theories and the integrability, we had a beautiful talk about eclectic spin chains in fishnets and non-diagonalizable Hamiltonian Jordan blocks and Polya enumeration theorem by Chang-Ri Man. Exciting talk about n equals 2 super formal theory and the dynamical spin models of elliptic type, which are maybe integrable. This was presented by Eli Pomoni. And then also we had this series of talks about the general aspects of integrability, like or the construction of beta vectors for SUN models and Haber model via the Drinfeld currents by Andrei Ilyashik. We had the results about the monodromy matrix for construction of the monodromy matrix for long-range spin chains, and a toy model for the rapid Lucier corrections in field theory. So a version of these Lucier corrections in the spin chains. We had a beautiful talk about generalization of classification and classification of various integrable models with new results on elliptic deformations of ADS spin chains by Anna Rettore. The geometry of beta equations and analytical structure of Q function by for any finite dimensional algebra in the talk of Dima. So we had, and then we had the talk about irrelevant deformation of CFTs, TT bar, and a study of a space of integrable theories, starting from the analysis of TBA equations by Lucia. And this morning we had the talk about the link between topological theories, construction of integrable model via topological theory with the example of background field theory and affine Godin models. Then we had this connection to other fields, applications of integrability to condensed matter in the talk of Takato Yoshimura about ballistic macroscopic fluctuation theory and long-range correlations for transport in integrable systems. We had talk about the relationship of CFT invariance and integrability, the properties of endpoint correlation functions in generic CFTs, partial wave decomposition relation to integrable models like Godin and hyperbolic Calogero-Sutherland in the talk of Ilya Buric. Then we had talks about bootstrap. So bootstrap appeared in many different guises in the conference. The bootstrap for in amplitudes and form factors, bootstrap of different functions. Then the conformal bootstrap, and then we had a talk about a matrix model matrix bootstrap and an interesting direction to build an alternative to Monte Carlo methods to compute quantities, interesting physical quantities in lattice gauge theory. And we had a talk about resurgence and in quantum field theory and the use of integrable models as a testing ground for ideas about resurgence and renormalance in the talk of Marcos Marinho. So, yeah, so talking about the resurgence, we hope that the field will also continue to have new ideas and create new directions, and for shorter term, I would like to announce the conference for the IGST conference for the next year. So it will take place in Zurich in June. It will be organized by Niklas and his colleagues. And Niklas wanted to emphasize that the conference will feature virtual and hybrid elements next to being a traditional conference. So with this, I would like to thank again to Zoli and the team, organizing team for the conference here, and to the participants, to the speakers for exciting and interesting talks, and see you next year for the conference in Zurich. Thank you.
Thank you very much. Thank you very much for the very nice summary. I would like to remind you that we actually have two prizes in this conference. The first prize was the best poster prize. We have a committee consisting of Romuald, Yannick. Actually, all of them already left. So Romuald, Yannick was one of them, Till Barger, and Wade. Yeah, Till is still here. Then why don't you explain it? So Till is still here, and also Wei Li. And then they had a very difficult decision. We had like 21 posters, and then they thought a lot, and then they took into account many different aspects. And then what they really appreciated is that if a poster brought up some new ideas, and then opened maybe a new research directions, and then was strongly related to the subject of the conference. And then they decided that the best poster prize should go to Daniele Gregory. So please, Daniele, come here, and then we should all thank. Yeah, please. We also have a prize for the best young speakers. It wasn't also an easy decision, as always. We have 6 speakers, actually. And the committee was a formal winner, actually, Fiona Zeibold. It was Alessandro Torielli and Fyodor Levkovich-Matyuk. And they decided that the best speaker's prize should go to Enrico Olivucci. So please, Enrico. There is actually a money prize which is given by the Gatis Plus, and then Gatis Plus will contact you, and then you will see how much. Also, Gatis supported some young speakers, so Gatis will contact those who got support, travel and accommodation support from Gatis, and then the way of the reimbursement. I also would like to actually thank the other organizers, because this was so complex event. Usually I organize myself, but it was beyond my complexity. So I would like to thank my biggest help first, István Vona. Maybe István, maybe you should actually all come here. Yeah. Also, George Linardopoulos helped a lot. Robin Oberfrank, please. Yeah. Yeah, just come. Tamás Páhoky. And David Fülepi. And but the biggest help somehow, which came from our project manager, who was the secretary, who took the job of the secretary of the conference, was Norka Kunz. So Ishti will invite her in a minute. Yeah. And we would like to thank her very symbolically, and later not so symbolically. Yeah. So let's wait for her. Maybe she disappeared. I told her she should wait until the end. Yeah. So we are thanking. Please, Norka, come here. Yeah. So, Norka, we wanted to thank symbolically, very symbolically for your work. So thank you very much. I also thank all the speakers for preparing for very nicely and presenting. All the participants for coming. And I hope it seems we didn't really have an outbreak of the COVID I was really afraid of. Hopefully you will not anything later, yeah. So in closing the workshop, I thank for all of you for coming, and I wish you a safe trip back home. And see you next year in Zurich. Thank you very much. Yeah.